Let's travel into the future and play a game of cosmic hide-and-seek. And see how the Fermi Paradox changes when humanity creates more advanced technology.
Engage.
Carl Sagan wrote in the movie Contact, "This is a unique time in our history, in the history of any civilization. It's at the moment of the acquisition of technology. That's the moment where contact becomes possible." But if there is hidden life out in the universe, is humanity looking for it in the wrong way? Or are we looking for the wrong things? Like trying to find smoke signals in the age of fiber optics. And an even bigger problem is the scale of time. It doesn't just separate us by distance, it flows differently across the cosmos. In the movie Interstellar, 1 hour on Miller's planet is 7 years on Earth. So if there were a civilization on such a planet near a crazy massive black hole, and they were 100 years away from inventing radio telescopes, allowing them to transmit and receive data, how long would that 100 years be on Earth? 6.13 million years. And so how will the Fermi Paradox change the further into the future we go, and more advanced technology is introduced into the equation? This is the most exciting thing, that any single future technological breakthrough could dramatically change our understanding of there being life in the universe. For example, when humanity develops more advanced quantum-enhanced signal detection, we might discover transmission patterns that our classical instruments mistook for background noise, and suddenly finding galaxies full of artificially engineered quantum signals. Future technology will rewrite both the Drake equation and the Fermi Paradox. And while the Drake equation estimates how many civilizations could exist in the universe, but what is the likelihood that humanity is even capable of detecting them? How far can humanity look out into space? And what are our technological limitations? Are we able to see underground on other planets? At the same time, will our technology even be compatible with advanced alien tech? Does this mean there needs to be another calculation, say the detection probability equation, showing what's the likelihood that humanity is able to detect alien life at a given time? And does this create a new paradox? Because if future technology advancements increase the number of possible cosmic civilizations, could it also decrease humanity's ability in detecting them? For example, if it is proven that life can exist in subsurface oceans on other planets or moons and without surface signatures, this would increase the Drake equation result, the number of possible civilizations in the universe. But humanity's telescopes can't detect subsurface biosignatures, and so making these worlds appear lifeless to our current tools, and reducing the probability of detecting them. Or what about the possibility of building artificial habitats, making even uninhabitable planets places that can support life? But the problem is, these engineered ecosystems could also be designed to be self-contained, showing no signs of traditional biosignatures. This is the detection paradox. It occurs when our knowledge and theory advances, proving something is possible, but our technical capability hasn't caught up and is unable to detect it. This creates a gap between what we know could exist and what we can actually detect. Just like how black holes were mathematically predicted in 1916 by Carl Schwarzschild using Einstein's general relativity, but they were only first detected in 1971 through X-ray emission observations of the binary star system Cygnus X1. And then their gravitational waves were detected by LIGO in 2015. And now, more than 100 years after first being predicted, the first direct image of a black hole, M87 star, was captured in 2019. This ends up creating a cosmic game of hide-and-seek, where the better we get at searching, the better others might be at being invisible. This is the detection paradox. But let's go deeper. Let's start by breaking down the Drake equation and how future technology such as advanced telescopes, artificial habitats, and terraforming could actually change the nature of some variables, not just their values. This is the Drake equation. It is a mathematical framework to estimate the number of alien civilizations in our galaxy. So R star is the star formation rate. This is fairly well established at about 1 to 3 stars per year in our galaxy, and is unlikely to change dramatically with more advanced technology. And F planet is the fraction of stars with planetary systems, which is around 1, nearly 100%. This estimate has already changed dramatically due to Kepler data. Originally, Drake used 0.2 to 0.5. Now we know planets are common, and future technology like the successors of the James Webb Space Telescope will refine this further. So N-Earth is the number of habitable planets per system. It stands at about 0.4, but could change significantly with better detection technology. This is where advanced technology could radically change the equation. Our current definition of habitable is very Earth-centric. But in the future, quantum computers and advanced spectroscopy technology will simulate and analyze exoplanet atmospheres, and humanity could develop detection methods for subsurface oceans and build a greater understanding of extreme life forms. And so we might find that the term habitability is much broader than we thought. And if humans are able to terraform and build artificial habitats on inhabitable planets, aka Mars, then this N-Earth number will increase dramatically, as it would not be limited to naturally habitable worlds. This could make any planet potentially habitable. So the N-Earth variable might need to be reconsidered or be absorbed into a broader habitability potential variable that includes artificial habitats. And now, F-life, which is the fraction of planets where life emerges. This could change drastically if we find life elsewhere in our solar system. Future technology could allow humanity to detect biosignatures from exoplanets and enable the exploration of places like Jupiter's moon Europa or Saturn's moon Enceladus. In the future, humanity could have a better understanding of abiogenesis, which is the theory that life on Earth emerged from non-living chemicals through natural processes. One major discovery here could completely change this F-life variable. And could the development of advanced genetic engineering mean that life can be created on otherwise lifeless planets? Moving on to F-intelligence. This is the fraction of life that develops intelligence. And a better understanding of cognitive evolution and potentially discovering simple life elsewhere could help humanity estimate this better. And then F-civilization is the fraction that developed detectable technology. This is where the Contact movie quote becomes relevant. As we develop new technologies, we also develop new ways to detect those same technologies in other civilizations. For example, radio astronomy led us to searching for radio signals, and then our use of lasers led to looking for optical signals. And in the future, advanced gravitational wave detection might reveal new signal patterns, and other new technologies could open more detection possibilities. And the final variable is the length of time civilizations release signals into space. This is perhaps the most crucial variable that our technological development might influence, because if humanity develops technology that allows civilization to survive in unimaginable ways, such as super AI, digital consciousness, or multiplanetary existence, then this will greatly increase the variable of length of time that a civilization could release signals into space. And so the Drake equation tells us there should be countless civilizations out there. Therefore, we should see evidence of their existence everywhere we look. But we don't. We hear nothing but silence. This is the Great Silence. Imagine being in a quiet ocean at night. You know there are thousands of ships out there because you have done the math based on registered vessels, shipping routes, and maritime traffic. But when you look around, you see no lights, hear no engines, detect no radio signals. There is nothing but dark water in every direction. The darkness isn't what's strange, though. It is that you know the ocean should be full of running lights and radio chatter. This complete silence, when you know there should be so much noise, is chilling. Are all the ships running dark? Are they using some form of communication, such as underwater communication, that you can't detect? Have they all sunk? Or was your initial calculation about the number of ships wrong? So then the Fermi Paradox asks a simple question. Where is everybody? This contradiction between probability and reality has haunted scientists for decades. Technological advancement makes the Fermi Paradox even more intriguing. As humanity develops better detection methods and still finds nothing, it either suggests A. We're looking in the wrong ways, B. We're looking for the wrong things, C. There is something profoundly unique about Earth. Or more worryingly, there is a potential universal limit that could affect all civilizations, including ourselves. Meaning the problem could be some barrier or challenge that prevents civilizations from advancing beyond a certain point or surviving long-term, such as our technological advancements in the form of artificial superintelligence or advanced weaponry that leads to civilization destruction. Or maybe there is some fundamental physics limitation that makes interstellar travel or communication impossible beyond a certain point, barriers that we have not discovered yet. So then what is the likelihood of humanity discovering cosmic life? This is where a detection probability equation comes in. This equation asks 4 simple questions. 1. Are they within our detection range in space? 2. Do we exist at the same time, and will their signals reach Earth during humanity's existence? 3. Can humanity's technology detect life in different cosmic environments? And 4. Is their technology compatible with ours, or are they too advanced to detect? And so while the Drake equation suggests how many civilizations exist, the detection probability equation could explain why we haven't found them. Even with a high n from the Drake equation, we could have a very low d detection probability. This is the detection probability equation. It takes the Drake equation's output of n, the estimated number of civilizations, and then applies factors like technological limitations and gives an estimate of what are humanity's chances of finding cosmic civilizations. So let's see how technology in the future will change the odds of detecting life in the universe. Now, detection range is how far out in space we can detect signals. The further we can see, the higher this number. Because in the future, as humanity develops advanced space telescopes and sensors, this increases the detection range. Also, advanced AI and quantum computing will improve our ability to process signals, while space-time manipulation detection sensors will add new detection methods. And then time overlap is whether signals from ancient, extinct, or current civilizations reach Earth during humanity's technological period, accounting for light travel time from distant sources. A higher number here means perfect overlap of civilizations existing at the same time. Because the problem is, humans have only had radio telescope technology capable of receiving data for under 90 years. Carl Jansky first detected radio waves from space in 1931 using a radio antenna array while working for Bell Labs. This discovery led to Grote Riebe building the first dedicated radio telescope in his backyard in 1937. This also means we have been unintentionally broadcasting strong radio signals into space for only about the same time. This is a relatively short period in the grand scheme of cosmic time. The fact that we've only been looking for under 100 years directly affects the time overlap because it represents just a tiny window of time in which we could detect other civilizations. As we continue searching for longer periods, we increase the potential temporal overlap with other civilizations that might be out there transmitting signals. But this window will always be very narrow. Moving on to technological limitations, which is humanity's ability to detect life in different cosmic environments, with a higher number meaning we can detect life in more possible scenarios. Right now, humans can detect techno-signatures such as radio signals, optical emissions, including lasers, infrared signatures, and certain atmospheric biosignatures. But we are not able to detect life deep under planetary surfaces, in subsurface oceans, or subterranean environments, or through Venus-like planets with thick cloud layers and dense atmospheres. And there could also be dark biospheres with life who don't use photosynthesis, instead using different chemical signatures we might not recognize. And the last variable in the detection equation is path divergence and technological compatibility. This is the technological compatibility of other civilizations with humanity, where a higher number means the closer other civilizations are to humanity's technological path, making it easier to detect, and a lower number means their technology is beyond our detection capabilities. In the future, when humanity develops long-range quantum sensors, we will be able to step up a level and detect quantum-engineered structures, such as structures designed for quantum computing, quantum communication, or even energy generation based on quantum principles. But while one civilization, such as humanity, might focus on quantum technologies, another could go down the path of developing artificial biological networks. Two civilizations need to be using compatible technologies and at the same time to detect each other. We might only ever be able to detect civilizations within 1 or 2 technological steps of our own level. So advanced civilizations might be aware of us while remaining undetectable and winning the game of cosmic hide-and-seek. This means that probability of detection could drop further even with extremely advanced technology. And so, we might need to categorize civilizations by their technological phase. And the compatibility between these types would affect the equation factor, path divergence. This technology compatibility would help explain the Fermi Paradox. So we might be surrounded by civilizations, but we are using incompatible technologies for detection. It's like having a radio receiver in a world of fiber optics, so you're not going to pick up any signals, but that doesn't mean no one is talking. So this detection probability equation adds in humanity's progress with technology, and with future technology, our detection capabilities increase, but only for civilizations at our level of development. This is the reality of cosmic hide-and-seek, where the hiders could have a billion-year head start on the seekers. But how far ahead could other civilizations be? And how far away is humanity in catching up to these advanced entities? Because in the near future, using technology already in development, we have biosignature pattern recognition, which uses advanced spectroscopy for detecting engineered biospheres. So this would show signs of highly organized biological systems on planetary scales and could reveal terraformed worlds or artificial ecosystems. And 2, there is also gravitational wave pattern recognition, using advanced LIGO-type detectors that could detect artificial gravitational wave patterns, revealing possible civilizations manipulating space-time for travel or energy, and detecting megastructures and engineered solar systems. And in the medium future, there is technology that requires significant advances in our understanding of fundamental physics, but already has some theoretical basis, such as dark matter detectors that would look for artificial manipulation of dark matter, where signs of unexplained voids or concentrations in dark matter distribution could act as evidence of artificial universe manipulation. And then, artificial space-time curvature sensors could be used to detect engineered modifications to space-time, where regular geometric patterns would be signs of civilizations using space-time manipulation for travel and energy through wormhole networks or artificial space-time domains. And vacuum energy fluctuation monitors would be used to detect power generation on massive scales, such as Dyson spheres, Dyson swarms, and harnessing energy from micro black holes. And then, in the far, far future, this final group ventures into more speculative territory that would require changes in our understanding of physics and consciousness. Meaning, consciousness field detectors would be looking for signs of patterns in theoretical consciousness fields, detecting large-scale organized conscious activity and revealing totally different forms of intelligence. But this intelligence could exist as pure consciousness, with non-physical existence, therefore being mistaken by Earth as anomalies within natural quantum fields. Or will there be multidimensional scanning that could show unexplained energy-matter transfer between dimensions, revealing civilizations operating beyond our 3+1 dimensions? And what about temporal anomaly detectors that would search for signs of manipulation of time itself, and so revealing localized time dilation effects or temporal bubbles, which would be evidence of civilizations with time manipulation technology? But these future advances in technology will also pave a path towards the detection paradox, where if Dyson sphere technology is proven possible, then civilizations could already be harnessing an entire star's energy, making interstellar space colonization more feasible, and dramatically extends a civilization's lifespan, which is the L in the Drake equation. But it could also make detection harder by masking stellar signatures we look for and make star systems appear dark, while advanced Dyson spheres might be indistinguishable from natural phenomena. Another example is when humanity is able to digitally upload human minds. This would prove that other civilizations might be further ahead, living in a digital existence with a near-infinite civilization longevity. But by having no biological constraints, there will be no biological signatures to detect, and they might operate at timescales we can't perceive, either much faster or slower, making them invisible to us. And what makes these advanced technologies potentially reality-shifting is that each one could open up entirely new detection spaces we haven't considered, and reveal civilizations operating at levels we haven't imagined. Any one of them could show that the universe is actually teeming with life, using technologies beyond our current understanding, and completely redefine what we consider as intelligent life. But we might only be able to detect civilizations in our own technological phase, so ancient cosmic civilizations might have already passed and are no longer detectable, while today, galaxies could be full of advanced civilizations using incompatible technologies. And so the game of cosmic hide-and-seek continues, as future technology creates both solutions and new mysteries. And when humanity proves that life could exist in ways we never imagined, the universe becomes full of new possibilities. The first, second, and third volumes of the Encyclopedia of the Future are available on Patreon.